Advanced well architectures can improve reservoir access and production performance, but the regulatory question is broader than whether the well can reach the target.
The central test is whether the well can be designed, drilled, operated, monitored, and eventually decommissioned while maintaining integrity, environmental protection, asset protection, and compliance.
That starts with trajectory control. Directional drilling depends on accurate planning, reliable surveying, and continuous steering against the approved design envelope. A target is not only a point on a drawing, it can be expressed as distance and azimuth, or converted into north-south latitude and east-west departure.
So the mathematics becomes part of control assurance.
Correct. For example, a target at 500 meters along a 29-degree azimuth converts to approximately 437.31 meters north and 242.40 meters east. North and east are treated as positive values. South and west are negative values. That convention allows the planned target, current position, and correction requirement to be compared consistently.
And if those values are wrong, the well may appear compliant on paper while drifting outside the intended control envelope. As well architecture becomes more complex, that control envelope becomes more important. Horizontal, extended reach, multilateral, and hydraulically fractured wells introduce longer sections, more interfaces, and more exposure to uncertainty.
Exactly.
The regulatory view is that a complex well should not be assessed as simply a longer conventional well. Its specific risks and controls need to be demonstrated.
The target boundary calculations support that demonstration. The target center may be clear, but the operator also needs to understand the high side, low side, left side, and right side of the target circle.
That is where the radius becomes operationally important.
Yes, if the target radius is 30 meters and the center is 500 meters along the planned azimuth, the low side is calculated at 470 meters and the high side at 530 meters along that same direction. The left and right sides can be calculated using right triangle geometry or by offsetting 90 degrees from the target center and adding those rectangular coordinates back to the center point.
Using two methods also provides a check, which matters in a compliance setting. Collision avoidance is the next major control issue. Safe separation must be maintained from existing wells and relevant subsurface features. Collision risk is not limited to physical contact. An unexpected intersection can compromise casing integrity, well barriers, and future intervention options.
That links directly back to survey quality.
It does. Anti-collision planning relies on knowing the well position with sufficient confidence. Survey management and early deviation detection are therefore part of the risk control system, not administrative extras.
The same principle applies during target approach. As the job progresses, survey latitude and departure are subtracted from the target boundary points to determine distance and direction to each constraint.
And that tells the drilling team whether corrective steering is required.
Precisely. The material makes one point especially clear. Calculations must use data extrapolated to bit depth, not merely survey depth. Vertical section and true vertical depth calculations then help convert the target approach into inclination and measured depth requirements. The process compares current true vertical depth and vertical section against the target. The differences are used to calculate the angle and measured depth to the target center, high side, and low side.
So it is not only horizontal positioning.
Correct. The well must arrive within the lateral target limits and within the required vertical relationship. Remaining true vertical depth and remaining vertical section together define the required inclination.
That is where integrity risk becomes more visible. Long horizontal sections can increase torque, drag, and casing running challenges. Multilateral wells add junctions and completion interfaces. Each additional interface is another location where integrity needs to be designed, verified, and monitored.
And reservoir optimization cannot override those limits.
Exactly. Horizontal and multilateral architectures may increase reservoir contact and enable production from multiple zones. But a design that maximizes exposure while creating unacceptable integrity or environmental risk is not an acceptable design.
The regulatory expectation is evidence-based. The well design should demonstrate that trajectory, pressure, barriers, collision potential, well control implications, and architecture-specific integrity risks have been considered.
Evidence also has to be traceable.
Yes, records should show how the well was designed, what assumptions were made, what surveys were used, what barriers were established, and how integrity was assessed.
Controls and monitoring complete the chain. Surveying, trajectory monitoring, barrier surveillance, and operational controls must be appropriate to the nature and scale of the well activity.
That is the complete life cycle view. Design the trajectory, control execution, verify barriers, monitor integrity, and maintain the evidence.
The key message is that advanced design creates value only when complexity remains controlled.
A successful directional, horizontal, extended reach, or multilateral well is not simply one that reaches the reservoir.
It is one that reaches the target while maintaining well integrity, environmental protection, asset protection, and regulatory compliance throughout its life.